Hello, my name is Jay Arora and I am a third year BTech student. Today in this video I'll be talking about hinge laws and transformers. So firstly, before discussing hinge laws, we'll be talking something about support vector machine, some conclusions that we should remember. So we all have studied about support vector machine classifier in which we use hyperplane and margin values. So in this figure that we can see, these red points are the data points of class 1 and these blue points are the data points of class 2. So this is the hyperplane, this is the margin, and we also know that the margin should be as large as possible so that we could get a good classification between the two classes. So the value of margin we calculated was 2 by mod of W, where W is the weight and B is the bias. Uh, and we should also calculate about the loss function that plays a major role in case of our support vector machine. So let us first discuss about the soft and the hard margin. So this is the case of hard margin and this is the case of soft margin. So in soft margin we have some data points in between the margin value, and in this hard margin we do not have the data points in between the margin value, and there are the data points at the hyperplane values. So this is the soft margin case and we will be discussing about hinge loss in this soft margin case. So the importance of loss, it determines which parameters give the optimum result and which model is the best. Discussing about directly about what is hinge loss. The formula for hinge loss is L equal to maximum of 0, 1 minus ka yi into W transpose xi plus b, where the W transpose xi plus b, as we remember in SVM, that was yi hat, that was the value, and yi is the true value, yi hat was the predicted value. So this is the formula for hinge loss, and SVM minimizes hinge loss as we have studied. So what should we get from this equation? The given equation is, this is the value of loss function, that is the hinge loss, and this is the value of penalty. So hinge loss actually arise from the constant that come in the SVM, and constants were making sure that we should come on the right side of hyperplane as we know. So when we make correct prediction, the loss function value decreases, and whenever prediction is wrong, the hinge loss value is higher. How we can confirm it? So we can look at it with the help of putting values. As we know that for a correct prediction, the value of yi, that is the true value, should be 1, and the value of yi hat should be also be 1. So we can easily predict that whenever there is a correct prediction, the value of loss is 0 minus ka yi xi transpose beta, that is minimum value, and the value of whenever there is a wrong prediction, the value of loss function is 1 minus ka yi xi transpose beta, that is the value of hinge loss is higher. So let us move on with the graph which is between the penalty. This y-axis shows the penalty or loss size, and the x-axis shows the distance from the boundary. This shows the distance from the boundary, and left side shows the incorrectly classified, and right side shows the correctly classified data points. So this is the graph for hinge loss, and this is the distance. This is the distance from the boundary. In the x-axis we can see that, or we can easily see that in this side, that is the incorrectly classified data points, the hinge loss value is higher, and on the right side, that is the correctly classified data points, the value of hinge loss is lower. What can we infer from this reason? We can what we can infer from this region is, we can make correct prediction. The distance from the boundary is very small, hence margin is very small, hence there is some loss function. So we can also infer from this graph, this is same as that, of the hinge laws. So now coming on with the transformers, in simple language, we consider transformer as a kind of black box where we give some type of input and we get some kind of output, and here we have in between is transformer. This is a simple idea for considering it. Let us take an input of some language and we get the output of some other language. So input is given to the encoders and we get the output from decoder. Two separate layers are present inside the encoder. So this is a small diagram of encoder. Here we have self attention layer and feed forward neural network layer. These are the two layers that are present inside the encoder. So let us talk about first the self attention model. So weights are added, multiplied, and then bias is added. This is the diagram which we can see. In here, what we can infer from this diagram is, firstly, these are the words. Thinking is a word and machine is a word. These are dimensions are changed to from their actual dimension to 512, and this also their dimension is currently the dimension is 512. So this is multiplied with the matrix, that is wq. These are the weights, query weights, and then we get the result as q1. Then we once again I would like to tell, x1 is multiplied with wq, then we get the result as q1. X2 is multiplied with wq, then we get the result as q2. So these are the values that we get from the multiplication. Similarly, we can get k1 and k2. Similarly, we can get v1 and v2 from wk and wv. Then we calculate the scores by multiplying queries and keys. So score is now calculated. As we can see that the dimension is now changed. Once was 512 and now it is changed to 64, 64, 64, 64, 64, 64 from 512. So now the score values are calculated by multiplying query with the keys q1 k1 and q1 k2, and then we apply softmax activation function, and then we multiplying softmax values and calculating the sum. So now we calculated the final z value of self attention layer. So this is the yeah, so this we multiplying it and we get the q, and this we multiplying queries and k matrix. So then we combine all the z values. So what is z? Z is calculated by combining all the z values and multiply it by another weight matrix. One in detail, one detail in the architecture of encoder that we need to mention it before moving on to the each sublayer. In each encoder has a residual connection around it, as we have studied similarly in the ResNet, the residual connection. So we can skip layers like we can skip adding and normalizing layer, and we can skip directly to the feed forward, or we can skip it and then we can directly get into the add and normalize layer. So now let us study about this is a similar diagram. This was a diagram of encoder. So from the output of the encoder is fetched into the decoder. So this is the decoder, and the output gets into here, this encoder and decoder attention part. Now the output is passed into the linear softmax. The output of the decoder is passed into the linear, and then the output is passed into softmax, and again the output will be passed to the encoder along with another word as input. So again this output will be passed as input here, and another word output as input here also. So this is a short explanation about what is transformer.